Today we're going to start chapter 6, which is going to be applications of integration. And we're going to start with 6.1, area between curves. 6.1, area between curves. Okay. Let's first recall from Math 110A, section 5.1. In 5.1, we talk about how to find the net area under the curve. Okay. If the function f here is continuous on this closed interval a to b, then this area under this curve is called that a, and that is equal to, what do you guys recall what is it equal to? Well, that is equal to this integral of this function from a to b. Okay. So this integral corresponding to the net area under this continuous curve right here. Now consider this region that lies between these two curves, f and g. Okay. And between this vertical line, x equal to a and x equal to b, this region over here, this highlighted yellow region here, where f and g are continuous function, and with f greater than or equal to g for all x in a to b. So just as we did for area under the curve in section 5.1, we divide this region into n stripes of equal width, and then we approximate the ith stripe by a rectangle with base delta x, and the height to be f of xi subtract g of xi. Okay. So the Riemann sum will be this, is this sigma of f of xi minus g of xi, which is the height for this rectangle, times the width for this rectangle, which is delta x. So this is the area for this rectangle. So this Riemann sum is an approximation to what we think of as the area of this region. Okay. And this approximation will get better and better as we subdivide this interval from a to b into more and more subinterval, okay, as we take n go to infinity. So this approximation appears to become better and better if we take n go to infinity. So when we let n go to infinity, this Riemann sum is approaching to the area of this region, which is going to be, so the sigma notation becomes this integral notation. The xi over here, we're going to replace that by x. And the delta x over here is going to be replaced by dx. So this region that is between these two continuous curves is defined to be this integral of f of x minus g of x, and x here go from a to b. Notice that this function f is the function on top, function g here is the function at the bottom. So you're actually using the y coordinate of the top right here, subtract the y coordinate of the bottom right here, and integrating this, x go from a to b. So this is a formula for this area between these two continuous curves on a to b. Let's use this example to see how we use this formula here. Okay. Example 1, find the area of the region bounded above by y equal to e to the x, and bounded below by y equal to x, and bounded on the side by x equal to 0 and x equal to 1. Now first recall that the graph for exponential function, we use this, I make up this exponential fish to help you to remember the graph for exponential function. So when this constant base a here is greater than 1, say 2 to the x, e to the x, the graph is going to be exponentially increasing, passing this, write this up here 1. When the base a here is between 0 and 1, the graph will be exponentially decreasing, so will be this green part right here. Okay. Now if we put these two together and you add the head and the fin, so that looks like a fish, and I call that exponential fish. So that might help you to remember the graph for exponential function. Now this is e to the x. So the base is about 2.7, so it is greater than 1. So it's exponentially increasing, passing 1 here on the y-axis. Okay. So, and the y equal to x is this one. Now we try to find the area of this region right here. Now, according to the formula, this area here is equal to the integral of the function on top, which is e to the x, subtract the function down here, which is x, and x over here, starting from 0 and ending at 1. So integrate this e to the x minus x go from 0 to 1. Now we know the antiderivative e to the x, it is e to the x itself. Antiderivative of x is x squared over 2. So we just evaluate this from 0 to 1. That will equal to e minus 1/2 minus e to the 0 power. E to the 0 power is equal to 1. So simplify, we got e minus 3/2, or you can write e minus 1.5. So this is the area between these two curves. X go from 0 to 1. Okay. Example 2. We try to find the area of this region enclosed by this parabola, y equal to x squared and y equal to 2x minus x squared. Now we call from our function dense. Y equal to x squared is a parabola, so we go like this. Okay, so it's a parabola. And y equal to 2x minus x squared is again a parabola. However, because there's negative coefficient for this x squared here, it's a parabola open down. When you factor this, we found that x-intercept here will be 0 and 2. So we graph y equal to x squared here, and we graph y equal to 2x minus x squared over here with this 2x intercept. The vertex of this parabola here is between the 2x intercept. So it will be when x equal to 1. When x equal to 1, y will be equal to 1. We substitute. Okay. This is the parabola for this one. Okay. Now, in order to find this region enclosed by these two curves, we need to find the intersection point here. You can see that actually 0, 0 is one of the intersection points, but what about the other one? Okay. Now, to find this intersection point, we can solve this system of two equations together. To solve the system of two equations, we can use substitution method, okay? And then we can find the intersection point over here will be 0, 0 and 1, 1. Now, according to the formula, the area between these two curves is going to be the integral of the function on top, subtract the function at the bottom, and integrate this result here, x go from 0 to 1. Okay. X go from 0 to 1 because the intersection point here is 0, 0, 1, 1. So the x here go from 0 to 1. The first thing we do here is we will simplify this integral if possible. We can combine these two line terms right here. So combine them. So we get 2x minus 2x squared. To integrate this, we can take out this common factor 2. It's a constant multiple, so we can take it out. Now we find antiderivative. Antiderivative of x is x squared over 2. Antiderivative x squared is x cubed over 3. Now, when we do the calculation here, this is going to be 1/3. So you see this area over here is equal to 1/3. All right, so let's take a break.